I have in an earlier video talked about how when you have two resistance in parallel, in series, how they can divide the voltage applied across them into the ratios, the same ratios as the resistances. Now let me very quickly describe this again. Suppose that the voltage across those 2 points, say between here and here, suppose that the voltage across those points is V. Then suppose that these two are resistors with values resistances R1 and R2, and suppose that the voltage across R1 is V1, the voltage across R2 is V2. Now the idea here is that the sum of V1 and V2, V1 plus V2, must be equal to the overall voltage. The reason is because voltage, or the potential difference between these 2 points, is just the work done to bring 1 coulomb of charge, or a unit charge, from that point to that point. And V1 is the work done to bring the unit charge from there to there, and V2 from there to there. So this relation is just saying that the total work done is equal to the work done when you add up the work in each resistor, which makes sense. Then there are the Ohm's law equations in each resistor, where we have V1 is equal to I times R1, I being the current that flows through the resistors, and the V2 would be the same current times R2. V2 is I times R2. So that when I divide this, I get the ratio V1 to V2 is equal to the ratio R1 to R2. So as a quick example, suppose that the voltage of the battery is, say, 1.5 volts, and the resistances are, let's say this one here is 6 ohms. Suppose that the R2 there is 3 ohms. That means that this voltage, the V here, is divided into the ratio of R1 to R2, which is 6:3. So the voltages ratios are V1 to V2 is equal to 6:3, which is 2:1. In other words, this 1.5 volts is divided into the ratio 2:1. So it's like if I have maybe $1.50 and I divide between two friends, divide $1.50 between 2 friends in the ratio 2:1, how much would each of my friends get? So my friend V1 would get 2 out of the 3 parts. So 2 over 2 plus 1 times 1.5 is what my friend V1 would get. My friend V2 would get 1 part out of the 3 parts. So 1 out of 3 of the 1.5 total. Okay, so if we calculate this, we get 1 volt for V1 and half a volt for V2. So it's a fairly simple idea. just take this voltage, this overall voltage, and share it out in the ratio of the resistances. Now this idea of dividing up the voltage using resistance, or rather this setup, because it has this feature where you can divide a voltage up into two parts, has a name, right? This feature and setup has a name. It is called a potential divider, right? So this whole setup is called a potential divider. So a potential divider is just a setup that divides up a voltage into two parts, and in this setup you can control how much of each part, how you can control the ratios of the two parts by changing, say, the resistances. Now this makes it useful to if we want to maybe provide a certain voltage, a particular voltage, or adjust the voltage. For example, if I go to the shop and buy a battery, I would almost always see 1.5 volts. I might see maybe 9 volts or some other specific values. But if I suddenly decide that I like to have 0.7 volts, I can't just go to the shop and buy a battery that has 0.7 volts. So what do? Suppose I need this 0.7 volts to make some circuit for some very strange reasons. So what I would do is I would take this circuit. I would just go and buy a 1.5 volt battery. Then I could try and buy some resistors with suitable values and divide that ratio, that voltage up into the correct ratio to give me my 0.7 volts. But even then it is a bit tricky, because I might not be able to buy the correct resistors. I would imagine that, like batteries, if I go and buy a resistor, there are only certain specific values that I can buy. So if I really want to make a 0.7 or 0.3 volts or some other values from a given battery, what can I do? There is a way. So let me draw another circuit. Now the way is to use a long resistor. I suppose that I have a long piece of resistor, and suppose that it is not insulated, right? We can actually connect wires to this piece of resistor directly. So it's a material that has some kind of a conductor with resistance, and suppose that this whole piece of thing is in the shape of a uniform rod with a total say resistance of maybe 9 ohms. And suppose that the length of this is this has a length of say 1 meter. It's a length of 1 meter. So I still have my 1.5 volt battery, and this has a length of 1 meter. So this is different from having two separate resistors. Now I'm going to just have one long and narrow resistor. Now the trick here is this. If I'm interested in a particular voltage, what I could do is I could take a piece of wire and connect one piece of wire to one end of this long resistor, and I take another piece of wire and I touch it on somewhere along the wire. Now if I do this, I can think of this long resistor. I can think of this long resistor as having two parts. One part would be this part here. Another part would be this part here. So if I think of it this way, it is a bit like having two separate resistances, except that I'm free to slide this contact up and down and change the length of each part. Now what's the point of changing the length? Now recall something called resistivity that we have seen earlier. Something that goes like resistance is equal to the resistivity rho times the length of a piece of wire divided by its cross-sectional area. Now this refers to the resistance of a piece of wire with a length L, for example, and cross-sectional area A. So suppose that this is my piece of wire, for example, and that my L here is the length of this bit. So that's my L. And the cross-sectional area A is the cross-section of this wire, which is A. And the rho here is the resistance of this wire. So if I slide this contact along here, then the distance between these 2 points will change. And that means that the resistance between those 2 points can change. And since we know that the voltages are divided up according to the ratio of the resistances, if I change the resistance like that, right, if I slide this resistance will change and that resistance will also change, then that would also change the resistance between those 2 points. So if I call this V2, right, so this is V2 like this, and that's V1 like this. So that's V1. So what I can do now is to say, since the voltage, this voltage V, is divided up in the ratio of the resistance between these two parts, and since the resistance is in turn proportional to the length, so therefore the voltage V2 or V1, or say V2, will be proportional to this length, and V1 will be proportional to this length, and of course V itself will be proportional to the overall length. Okay, so if I say that, let me just write this out. If let's say this length here is L2, and that length there is L1, and this total length here is L. Okay, and the resistance is R1 and R2, as we've said here. I call this R1 and R2. So according to this formula, I would have said for R1 that would correspond to the L1, and for R2 that would be L2. So I can calculate R2 from L2 using this formula, for example. And likewise, for the full voltage, that would correspond to the full length L. So I can say have the total resistance R would be equal to rho times in this case the big L, the full length over A. Okay, so if I divide these two, I'll get R2 over R, this resistance, R2 over the full resistance, which is big R, is L2 over L, because the rho and the A cancel when I divide this. Now, but the ratio of the resistances, R2, this part, over big R, which is the whole thing, as you have seen from the earlier calculations, is proportional to the voltages across them. Alright, it's proportional, the resistance is proportional to the voltage. Now, R2 is related to V2, and the big R, the full resistance, is proportional to the overall voltage. So what we now have, therefore, is a relation between the ratio of the voltages and the ratio of the lengths. So this means that this means that the fraction of L2, the length of this bit as a fraction of the full length, would give us the voltage as a fraction of 1.5 volts. So before this gets too abstract, let me take an example and calculate some values from here. Just clear this part up. Okay, so suppose that I have this length here as 1 meter. Okay, and suppose that this battery, this cell, has a voltage of 1.5 volts. I now want to connect a piece of wire to one end of this long resistor and another piece of sliding wire that I can move around and touch it on somewhere in the middle of this, not middle, but some point along this resistor. And suppose that the length of this part is, say, 0.3 meters. So the question is then, what would be this voltage? I'll continue to call it V2. What is this voltage? Now I'll call that voltage V. So from what was said just now, the V2 here is proportional to the length. Okay, if I slide this all the way up here and change the 0.3 to 1 meter, then V2 would become just equal to V. Okay, so what I have here is a relation. Because the voltage is proportional to the length, then V2 over V would be equal to, now V2 corresponds to this length, 0.3. V here corresponds to the full length of 1 meter. So 0.3 over 1 is just a fraction of this length over the whole length. Okay, but this equation allows us to calculate V2 because we know what V is. V is 1.5. So therefore V2 is equal to the fraction of this length over the whole resistor times the overall voltage of 1.5. So all the previous algebra and reasoning boils down to this simple relation. All I need is to take the fraction of this length and multiply by the full voltage. That will give me the voltage that comes out from those two contacts. Okay, and in this case, if I take 0.3 times 0.5, let's see what we get. It's 0.45 volts. And the important thing about this setup is that I can easily slide this contact up and down. If I say change this from 0.3 to 0.4, then I can just change this calculation here, the number in this calculation to 0.4, and I can calculate another value. So therefore this voltage coming out can easily be adjusted. So if I want 0.7 volts, for example, from the 0.5 volts, all I need is to shift this up until this becomes 0.7 volts. But what would be the point of such a thing? Well, this thing, it has very wide uses. For example, I could connect this part to a light bulb. Then by sliding it up and down, I can adjust the voltage of my light and make it brighter or darker. And that's used as a dimmer, for example. If I use a dimmer, you can sometimes see either a sliding switch or some kind of a knob next to the light switch in the room, which you can rotate and make the light brighter or less bright. Or it can be used as a volume control in say a radio, or at least the older type of radio, where you turn the knob to make it louder or softer. So those are all based on this idea of sliding a piece of wire along a long resistance. Now this setup is basically a type of potential divider, but this setup makes it easier to adjust the voltage just by shifting the wire around. So this arrangement, this particular setup has a name, right? It's a special kind of potential divider. It is called a potentiometer.